So good morning and good afternoon. So we will continue our module 3, dry friction in static equilibrium problems. In the last class, we were doing problem on wedge friction. We just did one single problem on wedge friction. So today we will solve one or two more problems on wedge friction. Then we will solve a couple of problems on ladder friction, and that's going to end the module 3. And then we will get into module 4, which is very important module to understand section properties and rigid body properties, right? Yeah, so this is what is our action plan for upcoming lectures. And let me share my smart board for today's lecture. Hope you are able to see this board where this is of lecture number 24. That was last period what we were learning. We solved a problem on wedge friction. You know, wedge means it's a machine element which can be used to lift heavy load, or not lift heavy load, adjust the load. So compared to that of the load, the weight of the wedge is very small or negligible sometimes, and you would be able to lift the or adjust the load of 4000 Newton by magnitude of force P, which is smaller than that of 4000 Newton, and it can hold this system. So that is what is an advantage of a wedge. And you'd see that under heavy machineries, such kind of wedges will be kept. Whenever there is a precision alignment required, you would be able to apply a force on the wedge to make the adjustment in the machine or in the load, as we solve this problem. So in this problem, when we have solved, we were using that 3-force equilibrium whenever possible, so that Lami's theorem can be applied. And we got for the last class problem, the force P required to just to be applied on wedge in order to adjust, just to adjust the load of 4000 Newton is 2946.7 Newton. So this is the problem that we did. And today's class we will continue with the additional wedge friction problem, right? So this is lecture number 25. And today's date is 05/04/2021. Again, a problem on wedge friction. So look at this configuration. I have two blocks. One is a wedge shaped, another one is kept over the wedge. So this is block A of a wedge shape, and this block is A. And I have over this and another block B. B. And you see that the contact surfaces are not of same μs value. So here this is surface 1, and this contact is of surface 2. This is surface 2, let's call this is surface 2. And then surface 3 is here, it is rubbing against the vertical wall. This is surface 3 contact. So now mu S1 is 0.1, mu S2 is 0.2, mu S3 is 0.3, right? So there is a force P. See, now this angle here given is not a small angle like in the previous case we have seen. This is 30 degree inclination, 30 degrees angle. So now what would happen is this two blocks A and B, or A is a wedge and B is a load, can stay under static equilibrium? That's first question. Can you just investigate and say that can it stay at equilibrium? So A is a wedge, B is a block. The block B is weighing Q Newton. So there is a load on this, that is Q Newton. It's Q Newton. And there is a force P required here to be supplied or applied. So now determine the range of value of P. Question is determine the range of value of P for static equilibrium of the system. So any doubt in this question? So this is the question, and here wedge is not of smaller angle, rather it is of 30 degrees inclination, and the block is kept over it. So range of value of P is asked, means in absence of P, that load Q of block B can push this to the right. So you require a force P just to hold the wedge at the position, and you can increase the value of P so that you can just impede the load of B to move up. So this can be two states. So draw for both the condition and get the lower and upper value of P. So that is the condition. So let's consider case 1. Case 1 is what? Just to prevent the wedge to move left or right, to move when we see this to the right, move right. So what do you do? So the P is there so that this is not pushed on this side, right? So the tendency of this for this condition of case 1 stated would be wedges to move to the right, and that is being just held. So your friction direction should be opposing the expected impending motion. So draw the free body diagram. So let's draw first the wedge free body diagram. This is A. So in this I have now force P, right? And I have here the motion would be resisted by the friction. So what is the direction of friction? The direction of friction should be in the other way, so towards the left. So this is my friction force, and I would have here the normal. So this is N1, and here it is 0.1 N1. All right, and the wedge weight of the wedge can be neglected compared to that of this load. So it's not given, so you don't require to worry about the weight of this wedge A. So similarly, you would also have a friction force along the slope, and that would be of 0.2 times N2, and this is a normal there, N2. So these are the only forces that are acting now in this wedge, and the corresponding free body diagram of the block this is Q, this is block B, and the load there is its weight, which is Q. And look at now this contact surface 2 and this contact surface 3 here. So at contact surface 3, as this wedge is to impede to move to the right, that means this is going to lower down. So I would have here my friction force upward and the corresponding normal. So this is N3 and this is 0.3 N3 here. So whereas here it will be just opposite to this. So I would have here this is 0.2 N2 and this is N2. That's all. So this is free body diagram of the wedge and the block. So again, look at this wedge. Since the weight of the wedge is not given, that can be neglected. I have an advantage of combining these two, and I would have 3/4 equilibrium in this case. So this is going to be R1, and this angle would be now tan inverse of 0.1, right? So what is phi S1? Tan inverse of 0.1. So that value equals shift tan inverse 0.1. It's 5.71 degrees. 5.71 degrees. So this angle here is exaggerated. I have drawn. It's only 5.71 degrees, right? And similarly, I can also combine these two. And this is my R2. And now what is this angle to the normal? This angle to the normal is phi S2. So phi S2 would be tan inverse of, there the mu value is 0.2. So 0.2, that's going to be shift to tan inverse 0.2. So you have 11.31 degrees. 11.31 degrees. So this angle is 11.31 degrees. Right? Already this normal is having an inclination to the vertical 30 degrees. That you have to see again. See, if I draw this vertical, since this angle, wedge angle is 30 degrees, so this angle is already 30 degrees. And now this angle is what you have got as phi S. So I have R2 direction to the vertical is 30 minus 11.31, right? Yeah. So this is an advantage of representing combined as a resultant of your friction force and the corresponding normal. So what would happen in this case, in this free body diagram? So whatever that I have here R2, that would be same here. So when I combine, I will have R2. So this R2 will have here this 11.31 degrees, whereas that will have to the vertical this angle would be 30 minus 11.31 degrees, right? And I can combine here these two. So let me put it in this same color. So that's going to be, if I combine this is my R3, and this direction to this normal. Here normal happens to be N3 is horizontal. So this is phi S3. So I would have phi S3 is tan inverse of 0.3. So that value would be shift to tan inverse, then bracket 0.3. I have 16.7 degrees. 16.7 degrees. So knowing this all, now see it's become very simple. So I know this. And here again this load and this, there is no P. So here also three forces, here also three forces. So it's very simple to solve it by Lami's theorem, application of Lami's theorem. So how can I draw this conveniently? In this I require to get P, and I do not know R1, R2, two unknowns. Look at here, I have Q is known, load, and I have two unknowns here, that is one is R2, another one is R3. So I'll get R2 from this, substitute here, I'll get P value. So let me first get the free body diagram of the load of the block. So that would be, see how do I draw the same diagram? I expect that in examination you are drawing the detailed representation of this free body diagram with this friction force and normals, and combining them and so on, and then putting it for a convenient form, the load will be acting down, so vertically down. Sorry, this is slippery nowadays. Yeah. So this is Q, and this is my concurrent point, represent this block B, and I have now R2. So R2 to the vertical is 30 minus 11.31 degrees. So 30 minus 11.31 is what is 18.69 degrees to the vertical. So if I slide this R2 vector and get the tail here, so this angle to the vertical is what is now 18.69 degrees. Right? This is R2. Now R3 to the horizontal. So R3 to the horizontal. So let me draw this R3. That will have to the horizontal. See, someone audio is Venkatananda Reddy. Venkatananda Reddy, what time you joined the lecture? Venkatananda Reddy. You just don't join the classes in regular times and you come on your own vision, then disturb the class. You may leave the class. You're putting more effort and you're disturbing me. I will ban you completely throughout my class. So sorry, see, this guy has been sent out of the classroom, right? Okay. So if you're not following, you can ask. You can't put a music and then I think he's not attending the class. He's just been bothered about his attendance. I'm sure that these guys are keep on to re-register and do it, right? Anyhow, so let's not get distracted. So anyhow, he's sent out of the online class, right? Yeah. So now this R3 direction is how much? It is tan inverse of 0.3, that is 16.7 degrees, right? 16.7 degrees. So I have now this direction, so I can get now R2 from this. So once I have R2, then I can get what is my, here I know R2. So I can find what is P. So let us also draw the free body diagram of the wedge. So P is unknown, that is horizontal, that is to this direction. So that's P here. And you have R1. So R1, its angle to the vertical is 5.71 degrees. So this is R1, and this angle to the vertical is 5.71 degrees. This is R1. Look at R2. R2 direction to the vertical is 18.69 degrees. And that would be in this direction. This is R2. And that will have to the vertical 18.69 degrees. So that is all. So from this R2 I will know. I can find what is P. Right? Now let's again apply Lami's theorem on a block first and get to R2. So if I do that, R2 by sine of angle included by this, that is 90 plus this 106.7 degrees equals Q by sine of angle included here. So how do you get that angle? It's 90 minus 16.7. 90 minus 16.7 plus 18.69. So it's 91.99. So sine 91.99 degrees. So R2 equals Q sine 106.7 degrees divided by sine 91.99 degrees. So solving this, just a minute. Solve this and tell me the answer. Answer this. Sine 106.7. So it is 0.9584. 0.9584 Q is what is R2. So I got R2 now, very simple. And then substitute that in this. So now here I have R2 equals 0.9584 Q. So now solve here for P. So P by sine of angle included by these two, how much it is? So how do you get? So you can see that this 18.69 you can subtract from 180 degrees and add this 5.71 with the remaining. So 180 minus 18.69, right? 18.69 plus 5.71. So that's 167.02 degrees. So this angle between R1 and R2 is what is 167.62 degrees. So now this is all equal to R2, because R2 I know, divided by angle included here, that's 90 minus 5.71. So that is 84.29. So sine 84.29. Right. So now I can get P value equals R2. R2 is 0.9584 Q divided by into this goes on that side. So sine 167.62 degrees divided by sine 84.29 degrees. So solving this, I get P in terms of Q. So it's 0.9584 into sine of angle 167.62. This divided by sine 84.29. So I get 84.29. This is this is how much it is, 62 or 02? Just calculate that. So hot it is. Just calculate 180 minus 18.69 plus 5.71. So it's 0. It's 02. Please correct that. If I do that, so here it is 02. I would have here it is 0.216 Q. Right. So this is what is the lower limit now. Why this is called a lower limit? Because in absence of P, this block would not stay, will not hold the load. Rather, the load will push the block, push the wedge outside to the right side, right? So now, what would be the upper limit of the value of P so that this system is under static equilibrium? That means that the impending motion of load up is what is going to ensure that. So then what would be the changes in this problem? I would have the changes like this. So let me just take this picture once again. It takes the entire thing. Okay, so let us go to the second state. So there I have my wedge. This is case 2. So case 2 is what? Case 2 is just to rise the block B up. So just to rise means it is impending. It is not to move, it is the impending state. So impending state can be taken as a static equilibrium state. So I would have now my wedge 30 degrees. That would have now force P and see the direction of friction. So since it is to be moving to the left, it is pushed inside, then only the block which is there up on this wedge can be just moving up. So now the tendency of this wedge is to move to the left. So the friction force directions are, look at, unlike the previous case, it is to the right now. And this is my N1. So this is N1, this is 0.1 N1. I can combine this. Similarly, this is 0.2 N2 and I have N2 here. So this is the free body diagram of wedge A. Now the load given by block B, and this weighs Q, and just to rise up means now the direction of friction is down. So this is 0.3 N3 and I'll have normal here N3, right? And you see here the direction is just opposite to what is that you have drawn for the wedge. So first you have to always start drawing the free body diagram for the wedge. So now it will be just reversed. So the direction of friction here is 0.2 N2 and this would be N2, right? So this is that. So now I can again have this combining them. So this is going to be R3 and this, if I combine, this is going to be R2, and I know here this angle now R2 inclined, how much it is? 11 point. What was the angle? We were just did it in the previous. So we had 5.71, 11.31, and the third angle is surface friction angle is 16.7. So here it is R2. So R2 is 11.31 degrees. So this angle is 11.31 degrees. And you see here, interestingly, this normal to the vertical would be 30 degrees. So the direction of R2 is now 30 plus 11.31. So it's 41.31 degrees to the vertical. Whereas in the previous case, it was the difference, right? And here, what would be this angle? This angle is, say, 16.7 degrees. But the direction now is down. So I can draw a simplified representation of three concurrent forces to apply Lami's theorem. So this is Q, and I have now R2 is at an angle to the vertical given by 41.31 degrees. That's R2. And R3, this is horizontal, I would have R3 where this angle is 16.7 degrees, right? So now it's very interesting that I can have this angle, included angle 90 plus 41.3, 41.31, and here it's 16.7. So I can apply Lami's theorem. So what is that I needed in this? R2. So R2 by sine of angle included by this, that is 90 minus 16.7. So 73.3. 73.3, that's equal to Q by sine of angle. What is this angle? 90 plus 41.31 51.31 plus 16.7. So 148.01. 148.01 degrees. So this gives me what is the value of R2. So R2 will be Q sine 73.3 divided by sine 148.01 degrees. So that's equal to sine of this value reciprocal, multiply this with the sine 73.3. So I get Q is 1.81 times Q is what is R2. So R2 is equal to 1.81 Q. So now this simple, as we have done it in the previous case, I can again now move back to this wedge and represent that as a 3-force equilibrium. See, this problem, similar kind can be asked in the examination. So I have here now R2. So R2 direction out to the vertical, you see this R2, this friction angle plus this slope 30 degrees. This is 30 degrees. And this angle here is R2, that is 11.31 degrees, right? So that is what is 41.31 degrees, and that is to the vertical. So if I now represent this P from the concurrent point to the left, that's P, and this is my wedge point, and R2 is to the vertical, but it is down now. That's R2, that's equal to 1.81 Q just now we found, and this angle is what is now is 41.31 degrees. And now this N1 and point N1 can be combined, so this is R1. So R1 direction to the normal, here normal happens to be vertical, is 5.71 degrees. So I would have here R1 to the vertical by 5.71 degrees, right? So any doubt in this? Any doubt? Any doubt in this? So now we apply Lami's theorem and solve. So this is R1, and I require now P. So I can just get it now, P by sine of angle included by these two vectors. Sine, what is that angle? So that angle is this angle. It's 180 minus 41.31 minus 5.71 is 132.98 degrees. So that's equal to R2, that is 1.81 Q by sine of angle included here is 90 plus this, so sine 95.7 degrees, 71 degrees. This would solve for P. So 1.81 Q into sine 132.98 degrees divided by sine 95.71 degrees. So solving this, to 1.81 divided by sine 95.71. That is 1.33 Q is what is P. Right? So that is what is now completing the answer for this problem. So now, for the system to be under equilibrium, the range of value of P is given by P should be less than 1.33 times Q and it should be less than 0.2, greater than 0.216 Q. So this is the answer. So like this you should answer. So as long as you have P value between these two values, you would have this system under static equilibrium. So this type of problem can be asked in the examination. So this is of the group of wedge friction problem. Any doubt in this? Any doubt so far what we discussed? Priyansh?
No doubts. No doubts.
Just let me save this file. So this is lecture number. What is this lecture number?
25, sir.
25 or 27? 25, 26?
Maybe 20, 27 or 28.
27, correct? Last lecture we had 25 and 26, which I have saved.
So this is 27.
Yeah. Yes. So let me just take that lecture as well. 25, 26, what we were doing. So, no. 25, 26, this is my MTech class. Okay. It is only 25th lecture. My mistake I saved in this. Right? I had to correct that. So this is 25th lecture only. So save as. This is lecture number 25. It's lecture number 25 only. That's correct. Right? So 25, 26 I saved. This is the lecture for MTech class where we were doing today morning vehicle handling study. So you would see this type of equations are required to understand the handling behavior, right? So this is what is that we were doing in the morning lecture today from 7:30. So you see this all to do in an advanced course. You are supposed to be liking this rigid body mechanics. For this course, the prerequisite for vehicle dynamics courses, your rigid body mechanics. So if you are good at that, you would be able to handle any of the mechanical engineering course. So it's not only for mechanical engineering, it's also for any other discipline because it's a basic science. It gives you problem solving skill. It will give you an idea, aptitude that you will systematically look at the problem and start analyzing. So this type of capabilities are very much essential for any engineers, right? Okay. So this we did, and then we will again, I'll just stop recording and then again start as we will get into the next lecture, lecture number 26, right? So let me just stop recording.